Now let's move on to the next two folders, the ones that are for the bifacial solar cell and the one for Perk cell. So let's take a look at bifacial cell first. SolarEYE browses through the directory. It finds 4 samples this time. Well, let's take a look at them one by one. There's one called split 3 cell 09, and here I show a cross-section diagram of such a typical bifacial solar cell. There's another sample called split 3 front metal 02. This is a cell that has no rear printed grid, and I also show here the cross-section of this sample. There's another sample called split 3 rear metal 01. So this is a cell that has no front grid printed, and I also show the cross-section for this sample. And finally, then there's a cell which simply has no metal on either side printed, and I also show the corresponding cross-section of this sample. These 4 samples are specially fabricated. They're not too hard to fabricate, simply bypassing some of the metal screen print. The sample set is designed for SolarEYE to accurately separate contributions of metal-induced recombination on the front and rear side. So I'm just gonna align the blue bounding box a little bit better, as well as make it a pseudo square. So these bifacial samples are also 5 bus bars, so number of bus bars remain unchanged. We can keep using these regions of interest. So this time around for cell type, we no longer have just the finished cell. We have in fact N-type bifacial cell that brings up 4 sample possibilities corresponding to the 4 that we got. So the finished cell is split 3 cell 09. Cell without front grid is in fact split 3 rear metal 01. Cell without rear grid is split 3 front metal 02. And cell without grid on either side is split 3 no metal 01. Down below, because this is a monocrystalline cell, so there is no need to have non-uniform C or non-uniform J01. There's not going to be a whole lot of variation across the wafer face in the conversion factor, which is C, converting luminescence intensity into voltage. And there's not going to be a whole lot of variation along the face of the solar cell in recombination current. This time around, we cannot fit to contact resistance because so happen the finished cell does not have the appropriate bias PL images taken that enables SolarEYE to fit to contact resistance, so we simply don't, and the fitting will be purely to all recombination parameters. For bifacial cell, we have these additional checkboxes, whether we want to fit to front metal and rear metal J02s. Yes, we leave them checked. The rest will be the same. This time around, we have available VOC and fill factor values. So happen for this cell, we do have the VOC is 661, fill factor is 80.52% from the IV tester, and we check fit to VOC and fill factor. And let's just make a guess of J0E is 50 femtomes per centimeter square. The model we have to change, and this time we have model split 3 with rshunt.mat as our fit model. We can take a look at it. So here we are, our bifacial model. So we're ready to run job, but here I would like to introduce to you this option called Suns PL. It's just a way to have a pre-check of the data to see that they're in order. So let's click it and see what happens. So what Suns PL does is it actually browses through all the open circuit images of all the samples, convert them into voltage, and then plot the voltages against light intensity for all 4 samples. And this is what we call a Suns PL graph. So the important thing to check is that on this axis we have as x-axis VOC, as y-axis the log of the intensity. So curves that are further to the right have higher voltage. And we notice that the sample with the highest voltage is the cell with no metal. And then the cells with the intermediate voltages are the cells with only printed metal on one side. And then the cell that has the lowest converted voltage is the finished solar cell. And that makes sense because as you put on more and more metal layers, the metal-induced recombination goes up, and therefore the voltage should drop. And so this is often a very nice check before you run the fit to see that the data is in order. So we close this, and again we can run job. Great, so we're done, and the whole process took about 23 minutes. So through the rounds of fit, SolarEYE adjusted the values for J01 and J02 in the passivated region, J01, J02 in the front metal region, J01, J02 in the rear metal region, and then it also adjusted the edge and peripheral J0s in order to come up with a best simultaneous fit to all these samples PL images as well as the provided VOC and fill factor. So this time around, there is no spatial distributions that were used in the front J01 because that was unchecked. Also, contact resistance was not a fitting parameter, so it's not shown. It's not shown as a spatial distribution this time. The quality of fit is decent, however there is some difficulty in fitting to the known VOC as well as the luminescence images at the same time, because oftentimes there is some discrepancies between the IV tester VOC and the PL tester VOC. So when that happens, then it's impossible to perfectly fit to both, and since they're not in agreement. So sometimes there is such an issue, and the user is encouraged to make the adjustments to make sure that the IV tester reported VOC value is consistent with the luminescence imaging reported open circuit voltage value. So here the best fit corresponds to a cell with VOC of 656.7 mV, fill factor of 80.19%. Here's the loss analysis. Emitter recombination, as we had defined, is about 50 femtoamps per centimeter square. That leaves about 82 in the base. You can see that the front metal, which is the light gray, and the rear metal, which is the dark gray, they contribute actually quite a bit to recombination at open circuit. As for fill factor, most of the fill factor losses are from series resistance this time. This is not fit parameters. All these are provided from the starting point of the model. And then we go to the Griddler model, and we can also see those fitted parameters here. So once before, this is the best fit model, and from here on you could do efficiency improvement. You can use this as to predict other behaviors of the cell. So we have one folder left to do, and that is for the Perk cells and samples. So if we select this folder, we notice there are 3 samples this time. So the 3 samples are the finished Perk cell with the cross-section as shown here. There's also a sample which is the same but without the front grid printed. So that's Perk with laser D10, and it has the cross-section as shown here. And then finally there is one sample which is like a Perk cell, but it has no front grid and it has no rear laser opening. So there's no rear metal contact as well with the cross-section as shown here. So this sample has no metal contact at all. So this is analogous to the previous example with the bifacial samples. So with the Perk cell, we can also make 3 samples with different amounts of metal contact, and that helps us to separate out the metal-induced recombination as well as the edge recombination. So as before, I'm just gonna do a little bit fine alignment just to bring the blue bounding box within alignment with the image. So once before, this cell has 5 bus bars, so again we don't need to change number of bus bars. For cell type, this time we choose PERC or LBSF cell, and that gives us the option to pick which sample is which. The finished cell is PERC cell E22, cell with no front grid, that is PERC with laser D10, and then cell without front grid or rear laser opening, that's PERC no laser CO9. So let's use the same fit settings. We uncheck fit to VOC-FF because for this cell we don't have the known values for VOC-FF from IV tester. For the model, we pick Perk cell model with rear local. Let's have a look at it. So this is fine. And just as with the bifacial samples, it's a good idea to run the Sun's PL just to have a look at the Sun's PL curves of all 3 samples. Just to make sure that the black one with the highest voltage is in fact the cell, the sample with no laser opening or front grid. Yes. The red curve is the intermediate voltage, which is the cell with no front grid, and then the orange curve is the cell, finished cell. Yeah, so this is in the right order, so we're good to go. So let's run job. So the fit is complete. For the Perk cell, there's this additional rear local contact J01 and J02 which is fitted. As usual, we can take a look at the breakdown of contributing factors to VOC and fill factor. Now let's go to the Griddler model. For a PERC cell best fit, the base J01, which is in this case 178 femtoamps per centimeter square, is further broken down if you're familiar with the rear local contact calculator. So what it does here is tries to split it up further, this base J01 of 178.4 into contributions by the rear passivation, which is contributing SRV of 167 centimeters per second. And also contact SRV, which is 1457 centimeters per second, if you're familiar with these terms. And if you're not, I encourage you to learn about this rear local contact calculator from either the Griddler manual or there's a related video on it, because through this you can get an idea of how good your rear passivation is, how high is your rear local contact recombination, as well as do some optimization of the best rear laser opening pitch, and so on. Okay, so that brings us to the conclusion of this demo of SolarEYE workflow. We've covered the 3 example folders, one which is just a finished multicrystalline cell, one which is a series of bifacial cell and related samples, and one which is a series of PERC cell and related samples. And for each, we've done the SolarEYE fitting, in which the best fit parameters are automatically plugged into the cell model to enable the users to use them for further analysis and calculations.